Hello, everybody. My name is Alain Joie, and I'll be the chairperson of this morning. Welcome to this plenary session, the third plenary session. And I would like to tell you that we will have two talks in a row, and then we'll have a break, and then we'll have the third and final talk of the morning. So we will start right away with Maria Chudnovsky. She's a professor at Princeton. She's a specialist in graph theory and combinatorics. And she will tell us about induced subgraphs and tree decompositions. So please.
Thank you very much for having me. It's really my pleasure to be here. This conference was being planned for 2 years, and I'm so glad it's finally happening, and I'm so glad I could finally come here and enjoy Grenoble and see people and talk to you. On the plus side, I have 2 more years of math to tell you about. But on the minus side, 2 years is too long to wait. All right, so this is this right, or is this too loud? Is this okay? Okay. So this is going to be about work I've been doing with different people over the course of the last 3 years or so, and I'll mention which theorems belong to whom. But first, let me start with an introduction. Okay, so I'm a graph theorist. I think about graphs. Graphs have vertices and edges. And when you think about graphs, one thing to try and do is say, I'm interested in all graphs that don't contain some fixed graph, or maybe don't contain any member of some family of fixed graphs. And then you want to try and understand, what structure these graphs have, what properties these graphs have. But in what I just told you, there's something I did not make precise, and that is, what does it mean contain? Right? And there are many different containment relations you can think about when you think about graphs. There was very famous work in the 1990s describing the structure of graphs that don't contain a fixed graph as a minor, and somehow there a lot of topology comes in. But in the last 20 years or so, people started thinking about another containment relation, and that's the relation of induced subgraphs. And that's what I'll tell you about, and I'll explain what everything means. What happened? Aha, okay, it's fine. It changed its mind. Okay, so as promised, H is an induced subgraph of G. So let me first tell you roughly what it means if you can get H from G by deleting vertices. So what does it mean more precisely? The vertex set of H is a subset of the vertex set of G. And then once you decided what set of vertices you're looking at, you're not allowed to touch the edges. If two vertices are in the set you restricted to and they were adjacent in G, they have to be adjacent in H. Then we say H is an induced subgraph of G. So we have some examples. Let's see if I can be fancy here. So let's see some examples. This is G. This is an induced subgraph of that, because to get this from that, what you do is delete this vertex. This is not an induced subgraph of that, and the easiest way to see it, they have the same vertex set, but they have different edge sets. That's definitely not allowed, right? And I'm gonna, for those of you who care, everything's going to be up to isomorphism. So I say H is an induced subgraph of G, but really what I mean is G has an induced subgraph that's isomorphic to H. So the vertices are unlabeled. And we say a family of graphs is hereditary if its closed are taking induced subgraphs. And I have to say hereditary is such a good name for it. I'm so pleased that induced subgraphs grabbed that word before somebody else wanted it. Okay, so let's see what I'm doing. And a very well-known family of, a very well-known hereditary family is a family of perfect graphs, which, so it's always a pleasure to talk about perfect graphs in France, because that's where they were born, and that's sort of where a lot of the work on them was done, and this is really the place to talk about perfect graphs. So let me tell you what it means that a graph is perfect. So you know about graph coloring. You want to color the vertices so that if two vertices are adjacent, they get different colors. And then you can ask, how many colors do you need to color a given graph? And there's an obvious lower bound, which is the size of the biggest subset of pairwise adjacent vertices. That's called a clique. So if you have a clique of size 100, you need to use at least 100 colors to color the graph. Right, so that's here. Chi of h is the chromatic number, the smallest number of colors you need. Omega of h is the maximum number of adjacent vertices, of pairwise adjacent vertices. And so, as I said, chi is always at least omega, but the graph is perfect if these two numbers coincide, if the chromatic number is as small as it can get, right? And I want to say a little bit more, not just for the graph, but also for all its induced subgraphs. And that's for some reasons that I won't explain, but this definition was proposed by Claude Berge, a French mathematician, in 1961, and that was a great improvement of a more naive question when are chi and omega the same. So Berge made this, proposed this definition, and then he made several conjectures about these graphs. And it turns out this is a lovely, lovely class of graphs because suddenly, you know, all the things you could wish for become true. And in particular, Berge conjectured that a graph belongs to this family if and only if it doesn't contain certain induced subgraphs, doesn't contain certain graphs as induced subgraphs, and the description of the forbidden induced subgraphs turned out to be very elegant. So Berge conjectured in 2001, and then with Neil Robertson, Paul Seymour, and Robin Thomas, we proved it. What did they say? Berge conjectured in 1961. And with Neil Robertson, Paul Seymour, and Robin Thomas, we proved it in 2003, roughly. So a graph is perfect if it does not contain any odd cycles as induced subgraphs, and it doesn't contain complements of odd cycles as induced subgraphs. And here, by cycle, I mean length at least 5. A triangle is not a cycle for me. And okay, maybe I won't tell you exactly what these graphs are, but it's, you know, it's a nice, concise description. It's exactly two infinite families. And then Grouchy, Lowas, and Shriver noticed that another amazing thing is true for perfect graphs, and that is the fact that various problems that are NP-complete in general, you can solve in polynomial time if you know that the input is perfect. So among those problems is computing the clique number of the graph, right? Finding the biggest, the size of the biggest subset of vertices that are pairwise adjacent, and there are some other problems. But somehow it turns out these graphs, right, so they were defined by their coloring properties, and then it turned out they have a nice description by forbidden induced subgraphs, and then it turned out they have very nice algorithmic properties. So really, what else can you ask for? Okay, so inspired by this wonderful news, one might somewhat naively ask, do all hereditary families have nice properties? And unfortunately, the answer is not at all. So let me show you some ways in which hereditary families don't have nice properties. So for perfect graphs, the clique number and the chromatic number are the same, and for all induced subgraphs. What if I ask for much, much less? What if I ask that there is some function so that the chromatic number is at most this function of the clique number? Right? I know it's at least the clique number, but what if I ask it's at least 2 to the 2 to the 2 of the clique number? And turns out that's completely false. That's false for triangle-free graphs. You forbid a triangle, right? Very simple induced subgraph, and already you can construct graphs with arbitrarily large chromatic numbers. What about maybe algorithmically something good happens? Well, no. Computing the clique number is NP-complete for graphs with no stable set of size 3. So again, no hope there. There's one beautiful conjecture that I would like to mention that is, in some sense, tells you that excluding induced subgraph does something to your graph, and that's the Erdős-Heilen conjecture. So what does the Erdős-Heilen conjecture say? It's from, I think, 1989. For every h, there's an epsilon, so that if h is not an induced subgraph of G, then suddenly G has a huge clique or a huge stable set. What's huge? Well, it's the size of G to some power. Now, I read somewhere in order to be surprised by something, you need to know something about it. You know, who says n to some power is huge? Well, it's because if you look at a random graph, the expected size of the clique and of a stable set is log the number of vertices. So somehow, if you exclude any induced subgraph, you're very different from you know, the random graph that contains everything. Here it's log the number of vertices, here it's the number of vertices to some power. So this conjecture is open, it's been solved for some h's, but I'm not going to talk about that. Just for notation, Omega is the size of the biggest clique, and alpha is the size of the biggest stable set. And a stable set is a set with no edge inside. It's a set of vertices, no two of which are adjacent. Okay, so some hereditary families are very nice, like perfect graphs, and some hereditary families are completely terrible. So then the question is, which hereditary families are nice? When can you say something nice about a hereditary family? And right now I'm going to restrict my attention to two ways in which a family of graphs can be nice. One is when I can describe its structure, and another one is when I can design efficient algorithms for problems that are hard in general. I'm not going to talk about the chromatic properties at all. That's a whole other branch of research, but I'm not going to talk about that. Okay. So now, when you talk about structure and when you talk about algorithms, there is a concept that people have developed that really works well with both, and also worked well in the theory of forbidden minors that I mentioned earlier, and that is something called a tree decomposition. So what's a tree decomposition? It's a way to represent a graph using a tree. It's somehow a way to measure how close your graph is to being a tree, and let me explain what that means. So you have a graph G, and you're trying to construct its tree decomposition Tx. So T is a tree, any tree you like. And then there are a couple of rules. So first of all, you want to assign vertices of the graph you're decomposing to vertices of G. We think of it as hanging a bag on each vertex of the tree. So this is called the bag at V. They're not disjoint, they're not disjoint, they're not connected. I'm not telling you anything about the bags, just partition the vertices somehow. And then there are two rules. One rule is for every edge of G, it needs to be it needs to be in some bag. So you have to capture every edge. It's also true every vertex needs to be in some bag. I didn't write that down, but sort of more intriguingly, every edge needs to be captured in some bag. And then another rule is that if I look at the vertex of G and I see where in the tree it appears, it needs to appear in a connected subgraph. And so this is like there's some tension there. On one hand, you want the bags to capture enough of G, but on the other hand, you want to keep track of vertices of G. You want to make sure that every vertex of G somehow, you understand where it is in the tree. And that's what makes it a representation, right? When there are somehow two rules that go against each other a little bit. Okay, so that's what it says. Now let me do a couple of examples. So this is a tree. I'm going to try to construct a tree decomposition of it. So this is G. Now I'm going to use the same graph to serve as T. And now I just need to tell you how to assign the vertices of G to the vertices of T. And what I'll say is I designate a root. And then for every vertex here, I look at its unique path to the root, which it's unique because it's a tree. And then I look at a vertex and I look at its neighbor in this unique path. And the bag at this vertex is going to be it and its neighbor. So for example, here, I designated 3 as the root. I would say I'm looking at 1. 1, 2, 3 is 1's unique path to 3. 2 is 1's neighbor in this unique path. So the bag I'll assign to 1 is 1, 2. Here it is, 1, 2. So, and you can check it the same everywhere. Like for 3, for example, its path is just 3. So the bag at 3 is just 3. Now, it's very simple because it's the same graph, but there's also some confusion because it's the same graph. So I thought it's more helpful and simple than overwritten and confusing. I hope you agree. Okay, here's another example, less confusing. This is G. This graph is the tree, and I've written down the assignment of bags to the vertices of the tree. And you can check that every edge is somewhere, and you can check that every vertex appears in a connected subgraph. So that's another tree decomposition. And now notice that here the bags have size 2, and here the bags have size 3. And that's not a coincidence. I mentioned that we think of tree decomposition as a way to measure how far the graph is from being a tree. And what we mean by that is how big do you need to make the bags? And it turns out you can make the bags of size at most 2 if and only if your graph is a tree. So let me say something about that. So you're given a tree decomposition. Its width is the biggest size of the bag minus 1, because I don't know why. That was before my time. And then the tree width of a graph is the best width of a 3D composition. So you look at all the 3D composition of this graph, and you take the minimum of the widths of all of them, and that's the tree width of the graph. And we say G has small tree widths means it's close to being a tree, and it's somehow witnessed by the fact that the tree width of trees is 1. Okay, so that's a 3D composition. If this is your first time seeing it and you're not a graph theorist, it's probably not very meaningful. So then let's just remember it's some way to represent the graph as a tree, or using a tree. Okay, so now why do we care? Well, it turns out that if you are given a graph with bounded tree width, so that means it's a graph and you can find a 3D composition of it where all bags have bounded size, right? Size at most 100, size at most 1,000, then you can design efficient algorithm using a trick called dynamic programming. And the key thing here is that whatever problem you're trying to solve, you can look at every possible solution in a given bag. Right? Bags have constant size, so you can just look at all subsets. So that's one important thing, that the bags are so small you can just exhaustively examine all possible solutions in each bag. And then another sort of deeper property is that because it's a 3D composition, it is usually the case that if this is my bag and I understand the solution in this branch and I understand the solution in that branch, I also know how to find the solution in this subtree. All right. So the problems you can solve this way are optimal coloring, max weight stable set, some others. And I should just briefly mention, so we said this is for bounded tree widths, and then we said the key property is that you can examine all solutions in one given bag. Well, you don't have to be bounded size for that. If I can somehow promise to you that my bag is, let's say I'm solving max weight stable set, and I can promise to you that the 3D composition is into bags where each bag has at most polynomially many maximal stable sets, well, that's good enough, right? I just need to be able to look at all of them. The size was just a nice trick to do it. So people are thinking about 3D compositions where you're not trying to bound the width, but you're trying to somehow make it simple in some other way. For example, bound the stability number in every bag. And that I think is a very beautiful direction to go in. Again, I'm not going to talk about it, but I wanted to mention it because it's something I think is very important. Okay, so let's see. Okay, so but now that I've told you how much I like the idea of not thinking about the tree widths, I'm immediately going to go back to bounded tree widths. And I'm going to ask which hereditary families have bounded tree widths. So what does it mean? I look at a hereditary family of graphs, and I want to understand, is there a constant so that every graph in the family has a 3D composition where every bag has size at most that constant. And again, it's something that is well understood for minors, but for induced subgraphs, it's a different story. So, okay, but so if I want to understand when do you have bounded tree widths, the first thing I need to understand is when don't you have bounded tree widths, right? I need some examples where the tree width is big. So, and for that, we can definitely deep into the graph minor theory because, that they have theorems about that. They have graphs which have small tree widths and big tree widths. So what we learn from them is the following. Big cliques have big tree widths. Kn is n vertices all pairwise adjacent. And those have tree widths n-1. Big complete biped graphs have bounded tree widths. So that's you take two stable sets, each of size n, and put all the edges between them. Those have big tree widths, and so again, that's not good for us if we're asking what families have bounded tree widths. Then, so this is, somehow like this is a very dense graph. You expect them to be far away from being a tree, even intuitively. But here's another graph where, when you first start thinking about it, it's a little surprising. It's a nice cubic planar graph. It's called a wall, so I'm not going to explain what it is. It looks like this. You can make it bigger. And then you're allowed to subdivide all edges. So every edge here really represents a path of vertices of degree 2. And those have large triodes. How large? Well, it's the square of the size, right? In the first two examples, like here, the size was the triodes. Here, the triodes is about half the size. Here, the triodes is a square of the size. So again, it's big, right? If you contain a huge wall, then you know your triodes is not very small. It's a square root of huge, which is still big. Okay, and that's what happens with minors. That's all we could learn from the graph minor theory. But induced subgraphs is a somehow much more restricted containment relation. It's much harder for a graph to be an induced subgraph of something than to be a minor of something. And so here is another graph which has large triodes, which people, when people studied minors, they didn't need to think about it because as far as minors are concerned, this is contained in that. But as far as induced subgraphs are concerned, they're incomparable. So what is this graph? It's called the line graph of a subdivided wall. And what you do is you take this with its subdivided edges, and then every vertex of degree 3, you turn into a triangle, right? So here your junctions looked like this, and now I'm going to make them look like that. I'm going to make them look like triangles. And that's the line graph of a wall. And this is somehow exhausts what you learn from minors, in some sense. So now, as a first approximation, one might hope that this is it. That we've captured everything, but it turns out that's sadly not true at all. So a couple of years ago, Saint-Thierry and Trottignon constructed an example. Again, more French people involved. Constructed an example of a graph of a family of graphs that don't contain any of those abstractions, and yet you have graphs of arbitrarily large triodes in your family. And really, what they did, they constructed a family of graphs that don't contain K4, don't contain 4 pairwise adjacent vertices, right? So that's no. Okay, that's to counteract the first point, and they don't contain induced even cycles. So the induced cycle of length 4 is K22, so that forbids those. And then it's not very hard to see that the other two abstractions necessarily contain even cycles. So the family of graphs that don't contain induced even cycles definitely does not contain any of those abstractions. In fact, it's somehow even much more restricted than that. I think this is not in great shape. Thank you. Okay, so they constructed this family, which didn't contain any of the abstractions we mentioned so far, and had huge triodes. So we know that our first naive approach of just taking what we know from minors is not good enough. There are other abstractions. So, but then, one should look for other abstractions, but they also try to see how they can avoid their counterexamples. What special properties their family has that maybe we can avoid in some other way. So they noticed that in their family, graphs with huge triodes had huge degree, right? Saint-Thierry and Trottignon. And then they said, well, what if I ask about graphs of bounded degree? What if I say graphs with no even cycle and bounded degree? Is it true that then they have bounded triodes? And then the answer to that question is no. That was a theorem with my student Tara Abrishami and Kristina Vuskovic for every graph G in the family on top. So no even induced cycle and bounded degree. The triodes is bounded as a function of the degree. And I should mention that this particular question was asked by the group there, Abulker, Adler, Kim, Saint-Thierry, and Trottignon. And then they made a stronger conjecture that maybe for bounded degree, the abstractions from minors, the abstraction that I listed on a few slides ago, are enough. And that was open for a few years, but then a couple of years. But it was recently proved by Korhonen, which was a beautiful, very simple, very elegant proof. So I'm not going to tell you about Korhonen's proof. But I will tell you some ideas of our proof, just because our proof you can then massage to prove many other things. It somehow, as Korhonen shown, it was way too hard to prove what we proved, but on the other hand, it was rich enough to extract a lot of other things from it. Okay, so let's see that. Okay, so what I'm doing now is showing you ideas of the proof that graphs with no even cycles and of bounded degree have bounded trivids. So again, it's going to be quick and very hand-wavy, so don't worry. Okay, so what's a separation in a graph? A separation just means a partition into two sets. Oh, maybe I don't need to do it with my hands. I have the pictures here. It's a partition into two sets where the only edges between them come from the intersection. So in other words, if you delete the intersection of these two sets, then you can't get from here to there. Okay, and the order of the separation is the size of the intersection. Okay, so now when you think about even whole-free graphs, but also many other graphs with many other hereditary families, many other graphs with forbidden-induced subgraphs, there are some separations that come up naturally. And what I mean by some separations, the separations that have a lot of structure. In graph minors, you would focus on separations where the intersection doesn't have any structure, but it's small. In induced subgraphs, you can control the size generally, but you can say I understand what subgraph lives in the intersection between the two sides of the separation, and I can take advantage of that. So somehow this is the game here. In minors, they had size, and we have structure, and we try to somehow leverage that. Right? That ties into 3D compositions where the bag size is not bounded, but the bags have certain structure. Okay, so structured separations that occur naturally in even whole-free graphs are something called a star-cut set. That means you have a vertex so that you can delete it and some of its neighbors, and the graph becomes disconnected. So it's a separation where what's in the intersection is a vertex and some of its neighbors. Okay, so you have this star-cut set, and then you can build a separation out of it, right? So X is one side plus the cut set, Y is the other side plus the cut set. Okay, so we have that. Now let me tell you about another lovely theorem. So a CD separator in a graph is not a lovely theorem, not mine. A CD separator in the graph is a small set of vertices of size at most d, where if you delete it, the graph breaks apart into roughly equal size pieces. Now I'm very loose here with what I mean by roughly equal size. I just want to say the size of the pieces is bounded by some constant times the size of the graph. So like if I have one piece which is 2% of the graph and another piece which is 90% of the graph, that's fine as long as I can commit to bounded ratio between 90 and 2. Okay? So that's a CD separator. And by a theorem of Harvey and Wood, if we're trying to prove that something has bounded trivids, we can assume there are no bounded CD separators. I'm lying a little bit. There's something there with a weight function on the graph. And when I say at most 90% of the graph, what I should say is at most 90% of the weight. But for a plenary talk, this is good. OK, so that means whenever I delete a small set, the graph breaks apart in such a way that one side is huge. There's a connected component that contains, let's say, at least 90%, more than 90% of the vertices, and then the rest of the graph breaks into smaller pieces. And that is a good thing. That means there's a canonical separation I can define for every small subset of the vertices. So here it is. You look at the vertex. You can think of a canonical star separation. Remember, we're in bounded degree case, so you delete V and its neighbors. That's a bounded size set. As we explained, there's one component which is huge. And now the canonical separation that corresponds to this vertex, one side is the big side plus its attachments plus V, and it's important to include V. And then the other side is everything else. Or so, like this. Okay? So C is the attachments of the huge side plus the vertex I started with. Okay, so what the takeaway from this is, if I have a star cut set, which I have in even Hall-free graphs and many other hereditary families, there's a canonical way to get out a small order separation from that. And now two things happen. First of all, so I'm going to start with the second theorem. Leo already proved that if you don't have any star cut set, then the triwids is bounded. So that's very good. So then somehow, on one hand, I have this tool of star cut sets that I maybe can do something with, and on the other hand, if I don't have any star cut sets, then Leo already finished the work. So now let's focus on star cut sets. So again, in the graph minor theory, what you wanted was a collection of separations which had the property of something of being something called laminar. Let me not explain to you what that means, but it means somehow the cut sets interact with each other nicely. So in induced star graphs, we don't have that at all. I mean, for years, people were trying to understand what to do with this in natural separations for induced subgraphs that are not laminar at all. They just go crazy with each other. But it turns out that in this case, in the case of bounded degree, I mean, in the case I'm talking about, you can, first of all, there's some important star separations, which I'm not going to tell you what they are, but you can partition all the important star separations into boundedly many subsets, each of which is almost laminar. It's loosely laminar. And I'll show you what that means. So I would like a laminar collection of separations. I don't get that, but I get boundedly many collections, all of which is almost laminar. And that it turns out this is good enough. So let me show you something, and then I'll quit. So you can think about the star separation dimension of the graph, and that's how many loosely laminar collections you need to capture all the important star separations. And now it turns out you can do induction on the star dimension. So if star dimension is 0, that's less theorem, the triwids is bounded. Now you increase the star dimension, and you increase the triwids a little bit every time the star dimension goes up. But because it's bounded, eventually you've only increased it by bounded size, and you win. And that's an idea you can use a lot, as it turns out. So here's a picture, and this is the last slide in this proof, and then I'm going to chat again. So star separation dimension is k. Now I'm going to show you the inductive step. What you do is you look at one loosely laminar collection of star separations, and you intersect their big sides. Remember, a star separation has a huge side and a tiny side. You intersect all their big sides, and you call this intersection the central bag. So this big oval in the middle, big ellipse in the middle, is that. It's a central bag for this one collection of star separations. And now I can tell you what being loosely laminar means. It means that the rolled out side of the central bag breaks into components, each of which is a small side, or is contained in the small side of one of the separations you were considering. So somehow your graph has a huge center, and then little pieces hanging off it, and each piece attaches at the center in a very controlled way. It attaches at the center just on the star cut set. So now that's good for you. Now you can prove, right? So somehow you represent your graph in a simple way. And now you can prove all kinds of theorems. So you can prove that the central bag has lower star dimension than the graph you started with, which is good for you because you're doing induction. So the central bag definitely has smaller, definitely has bounded triwids. And then you can prove that the triwids of the whole thing is only a little bit bigger than the triwids of the central bag. Right? So the triwids of G is a function of the bounded degree, and C, which is how small these components are, and the triwids of the middle. And that's your inductive step, right? You describe the graph as something simple plus small bits attaching to it in a controlled way, and then you can prove a theorem that says the triwids of the whole graph is not much bigger than the triwids of something simple. And we call it the central bag method for obvious reasons. Okay, so now let me show you some other things you can do with the central bag method. And I'm not gonna prove anything. I'm just gonna wave my hands even more than before. So bounded degree, it was a nice place to start, but now Korhonen solved it, so it's really done. But even before, there's something unsatisfying in this assumption. So you want to see if you can go further. And so we're going to relax the bounded degree condition. Sentieri and Tratagnon had another bad construction, another construction that showed that our naive guess of what the abstractions for bounded treewidths are was incorrect. And that was this family. So let me explain to you what this family is. So it's a family of graphs that don't have triangles, right? So definitely no Kn. And they don't have subdivisions of K to 3. So K to 3 is a graph where you have 2 vertices and 3 vertices, and those are adjacent to this. And let me now move my hands and make a better representation of it. It's 2 vertices and 3 short paths between them. And a subdivision of that is just 2 vertices and 3 long paths between them. So you forbid all of those. The subdivisions of K to 3 are sometimes called thetas. So you forbid thetas and you forbid triangles, and you can check that that means you've forbidden all the abstractions I showed you earlier. And they were able to prove that you can get graphs like that of treewidth at least K for any K. So that's another piece of bad news. But then it was noticed that even though the treewidth is not bounded, it's not that big. It's only, like in their construction, it's only log the number of vertices for each graph. Now, why is log the number of vertices not that big? Well, remember, one sort of thing we want to do with 3D compositions is examine all subsets of a given bag. Well, if the bag has size log n, you can examine all its subsets in polynomial time, right? That's exactly what you can do with log n. That's where your limit is. So getting to its log n for at least for algorithmic purposes, logarithmic treewidth is good for algorithmic purposes. So it's not so bad for you. So this group conjectured that maybe if you exclude that, you don't get bounded treewidths, but you get logarithmic treewidths. And the answer to that question is yes. Okay, let me say something else first, just a minute. Right, so I'll explain why the answer to that question is yes, but before that, let me say something else. So remember, Sentieri and Tratagnon, they constructed a bad family, and then they said, well, but if I bound the degree, then everything is fine. So now you can maybe hope, well, if I don't require bounded treewidths, but I require logarithmic treewidths, then everything is fine. It's basic abstractions that we listed would always guarantee logarithmic treewidths. And that was a conjecture for a little while of Tratagnon, but turns out that's false because of an example that James Davis constructed recently. And it's this picture. You take many paths and then many vertices with neighbors in this path, and you can make this a little more general. So anyway, so possibly the current modification to this conjecture is exclude all of this stuff and exclude that. And then it's logarithmic. But I think at this point, we don't know. At this point, we're just collecting evidence. So it's an ad hoc conjecture. Okay, but something that Sentieri and Tratagnon did conjecture is that in the even whole free case, right? Remember the first case we talked about. If you forbid big cliques and big complete vector graphs, the treewidth is logarithmic. And that's still open. Okay, so but now let me go back to the question I mentioned earlier, which is a theorem, which is not a conjecture, and that's joint work, again, with my student Tara Abri-Shami and Sophie Sperkel and Sophie's student Seper Hajibi. Okay, so the theorem is roughly that if you exclude, so the conjecture was if you exclude thetas and you exclude triangles, the treewidth is logarithmic. We prove something a little stronger. Let me not read to you what it says, but basically you exclude thetas and you exclude some graphs that contain triangles, so something a little bigger than a triangle. And then the treewidth is logarithmic. And the proof method is the same as what I showed you in perfect graph, the central bag method. So what happens here, the star separation dimension is not bounded by constant, it's bounded by log the number of vertices. But our inductive step, what it does is it tells you at every step you grow by constant. So if you have log n steps and you grow by constant at each step, you get a logarithmic bound. The place where new ideas are needed, in the bounded degree case, the cut sets were bounded size, and that was very important. Here, there's no reason to you know, here we don't get that, right? You look at star cut sets, you look at the vertex and its neighbors, and it's huge. There's nothing to do about it. So you need to put a lot of work into this last bullet, which I'm not going to tell you about, but somehow it started in the same place. And but an important thing in this proof, which sort of it's one step away from the Evenhofer proof, from the bounded degree proof, but not 20 steps away from the bounded degree proof, is that the cut sets we're looking at are still connected. It's still the same star cut set. It's cut set that consists of a vertex and its neighbors. And a lot of the ideas we developed still work. Okay, let's see. Okay, so we had bounded degree and bounded triodes. We had bounded degree and logarithmic triodes. Now let's focus it even more. Now let's try, what did I say? Bounded degree and bounded triodes, unbounded degree and logarithmic triodes. And now let's go one step further. Let's try unbounded degree and bounded triodes, right? That's somehow the most general case. When can you bound the triodes without bounding the degree? Okay, so let's see what we know. Let's see what we have to exclude. So from the first construction of Saint-Hilaire and Trottignon, you have to exclude something called wheels. And what a wheel is a cycle, induced cycle, and the vertex with at least 3 neighbors in it. Saint-Hilaire and Trotignon's construction is full of wheels, so you know, really, to really hit it hard and not get anything like that, you should exclude wheels. Then from the construction of Davis, it turns out it's not enough, because in the construction of Davis, you don't have anything like that, but what you do have is those kind of things. So that's an induced cycle and works with 2 neighbors in it. Okay, so let's try that. But before we try that, let me tell you about the theorem of Login and Rasgon that tried to address the same question. What do I need to exclude in a hereditary family in order to get bounded triodes? And there's sort of a nice trick you can do. What if I say I'm only allowed to exclude a finite number of graphs? That really changes the problem. If you haven't tried it, it sounds, you know, graphs, it sounds like, you know, a little bit similar, but it's really very different, because what it tells you, for example, you can't say exclude H and all its subdivisions. That's not allowed. H and all its subdivisions is an infinite family. So you really, it gives you much more power. You can, you're thinking about a slightly different question. But on the plus side, it has much nicer answers. So a theorem of Login and Rasgon is the following. If you try to exclude a finite family of graphs, and you ask for which family is F3 graphs, F3 means you don't contain any graph in F as an induced subgraph. So when do F3 graphs have bounded triodes? Then there's a lovely answer to that. You need to exclude big cliques, big complete biped graphs, a graph that looks like this. So it's a forest where every component is a subdivision of K13, and the line graph of a graph that looks like that. And what that means is you replace this Claude junction by a triangle junction. Okay, so that's that. So now let me go back to not saying that I exclude a finite family, but remembering that I had to forbid wheels and I had to forbid something less general than wheels, which is a cycle and a vertex with 2 neighbors in it. So there's a name for that. A propeller is that. It's a cycle and a vertex with 2 neighbors in it. And turns out propeller-free graphs, so propeller-free means you don't contain any of those induced subgraphs, and turns out they have a nice structure. You can prove things about them. They were studied about 10 years ago by this group. And what that means for us is that we could try and use, right, so they prove that this family, that the graphs in this family have some natural separations. We can try and use our methods, our central bag methods, for the separations that they obtained. And that was sort of our inspiration. And then we had to reprove all their theorems, because we needed just a slightly more general statement, which really they probably already proved, but they didn't write it down. And so we had to do 5 pages of 5 pages of proofs that they probably knew about, and if only in 2012 we could tell them we needed them to write it that way, they would have done it, but. Okay, so here's the theorem. Now, so there are more authors. It's the same group, Abrishami, Hajibi, and Shperkel. And then we have 2 more authors here, Bogdan Aleku and Kristina Vushkovic. And the theorem is, for every T there is C, so that you don't contain any T basic abstractions. T basic means complete graph on T vertices, complete bipartite graphs with sides of size T, a wall of height T and the line graph of a subdivided wall of height T and the line graph of a subdivided wall of height T. And you don't contain propellers, right? Because we sort of argued that you better exclude them. Then the truth is bounded. And again, we prove something a little stronger, but let me not say what it is. And let's see. Okay. So what's the proof? And again, I'm only going to give you a very high-level overview. So first of all, there's some easy reductions you can make and reduce your problem to the case of triangle-free graphs with no star cut sets. And then it turns out that, so here's something called a heavy sigil. A 2H path in graph theory is called a sigil. If you draw it like this, it looks like a bird. And a sigil is heavy if the 2 ends have degree at least 3. So that's a definition from this paper. That's not something in graph theory. And it turns out that 2 things happen. If there's no heavy sigil, then the tree is bounded. That's not hard. But if there is a heavy sigil, then you get a decomposition that breaks it. For every heavy sigil, there are 2 cliques you can delete so that no component of what's left contains your heavy sigil. Now that's good for us. That's again some nice decomposition. A cut set of bounded size, and you can prove that. Here's a picture. Right? So the blue thing is a heavy sigil, and you can find 2 cliques so that the heavy sigil looks like this. And then it turns out that you can take all the separations that you found and partition. You don't even need to partition them into loosely laminar collections. Somehow you get lucky and they're already loosely laminar. So that trick is neat, but we don't need it. So that's very good news for us because we can now do the central bag method. Except now we need another idea, because in everything we've done so far with the central bag method, it was very important that the cut sets are connected. Really, it was a key property that you needed. But here the cut set is not connected. Here the cut set is 2 cliques. So you have to do something slightly different. And we struggled with that for a long time. We knew we had to make that step because most natural cut sets are not connected. But we didn't know how to do it, and this is the first time something came out, so I'm very pleased with this theorem. So what we ended up doing is changing the definition of the central bag slightly to include in it not just the cut set that you need to break the graph, but also a little bit more. Another pass of verts of degree 2 that remembers that this cut set, that you could get between the 2 components of this cut set outside of the central bag. And it doesn't mean anything to you if you don't do a graph structure, but it was a big step for us. Okay, and then once you understand how to do that, the proofs go through and you can do the same inductive step and all of that. And now this is my last slide. So we're still trying, we're still sort of searching in the dark and trying to find what can you exclude to guarantee bounded tree widths if you don't bound the degree. And we finally found this theorem, which is kind of neat and looks like the Login-Rasgon theorem, but stronger. So if you forbid all basic abstractions, and then you forbid a graph that looks like this, a graph that looks like that, and the difference between this and that is that here, versus of the, here you have claw junctions, and here you have triangle junctions. That's somehow a recurring motif. And you forbid that. So the degree is really 3. Then the tree is bounded. And this is proved by a completely different method, so we don't yet understand how that's related to to everything else we've done. And that's with the same set of authors. Let me stop here. Thank you very much.
Thank you very much. So are there questions or comments in the audience? Yes, please.
Well, there is this other notion of width, click width or rank width. Do you know anything about a similar question?
So it's a great question. And basically, the difference between tree width and click width and rank width are basically the same. But the difference between them is that for tree width, you need to exclude big clicks. But for click width, you don't need to exclude big clicks. My guess is that most of these should work for click width without excluding a big click. We haven't done it, but that's definitely kind of the next horizon. And in fact, some of the theorems are not our theorems, but some of the theorems that we've used here are known for click widths. Like, for example, Les' theorem, that even whole free graphs with no with bounded degree and no star cuts that have bounded tree widths, really what he proved is that they have bounded click widths, and then you can turn it into a tree width result. But yeah, that's exactly the right question.
Yes, are there other questions? Yes, I'm coming.
Thank you. Thank you for the talk. And if you take the characterization of tree widths, it's by square grid minors. If you take characterization of Gromov hyperbolicity, is via linear isoperimetric inequality, which is also about planar graphs, subgraphs, and therefore you can forbid, for example, basic abstractions. Big clicks and big complete bipartite subgraphs. And now suppose that all planar subgraphs of your graph have bounded tree widths, induced subgraphs. Can you conjecture that the tree widths will be bounded? So you have a graph without big clicks, no big clicks, no big induced complete subgraphs, and then all planar subgraphs have
so
bounded tree widths.
I think Davis's example, when you have many paths and then many vertices attaching to them, that might be a counterexample because that has K33 as a minor, so it's not planar. Mm-hmm. But if you contain that, you're not going to have.
Okay. Thank you.
Sure.
Thank you. Other questions or comments? So it doesn't seem to be the case. We can thank Maria again.
Thank you very much. It was my pleasure.